If you have ever observed rusted iron, tarnished silver, or the green patina that develops on copper or bronze, then you are familiar with corrosion. Corrosion is the term used to describe the process of the surface of metal objects getting covered by oxides or other salts of the metal. In corrosion, the metal is oxidized by losing electrons to oxygen, forming oxides. Corrosion is essentially an electrochemical process. Let's look at the corrosion of iron, which is commonly known as rusting, in detail. Iron corrodes in the presence of water and air. The spot where the corrosion begins can be considered the anode. Here, iron loses 2 electrons to form the iron II ion. The oxidation half reaction has an oxidation potential of minus 0.44 volt. The electrons thus released then move to another spot on the metal, which then behaves as the cathode. At this spot, oxygen is reduced in the presence of a hydrogen ion to form water. The hydrogen ions are believed to be available either from carbonic acid that is formed when carbon dioxide dissolves in water, or due to the dissolution of other acidic oxides from the atmosphere. The reduction potential for this process is 1.23 volts. In the overall equation, iron is oxidized to iron II ions, while oxygen is reduced to form water. The cell potential is 1.67 volts, consistent with a spontaneous reaction. The ferrous ions formed are then further oxidized by atmospheric oxygen to ferric ions in the form of hydrated iron III oxide, commonly known as rust. It is very important to prevent corrosion because it damages electrical towers, bridges, buildings, which can collapse as a result, and ships, which can develop a breach. Corrosion can also force major industrial plants, such as power plants or chemical processing plants, to be shut down. Hence, corrosion not only results in loss of money, but also endangers public safety. How can corrosion be prevented? One way is to cover the surface with paint or some chemicals like bisphenol. This creates a physical barrier that protects the metal. A second alternative is to cover the surface with other metals, such as tin or zinc. Like paint, this prevents oxygen and water from reaching the metal surface. We can also use electrochemistry to prevent corrosion. In cathodic protection, the metal is coated with another metal that is more easily oxidized. In cathodic protection of iron, iron becomes the cathode and the metal coating becomes the sacrificial anode. Cathodic protection can be used to protect steel pipes from corrosion. Magnesium oxidizes more readily than iron, as you know from the table of standard reduction potentials. In this diagram, a magnesium rod is buried and soldered to a steel pipe. Magnesium acts as the anode and the pipe acts as the cathode. The damp soil acts as an electrolyte. The magnesium rod can be dug up and replaced. This is much faster and less expensive than replacing the pipe itself. Try to answer this question on your own before proceeding. Based on the table of standard reduction potentials, which of these metals could provide cathodic protection to iron? Aluminium, copper, nickel, or zinc? Answer: aluminium and zinc could be used to protect iron from corrosion. As shown in the table, their reduction potentials are more negative than that of iron. This means that they are more readily oxidized than iron. Copper and nickel reduce more readily than iron, making them unsuitable for cathodic protection.
The electrochemical series is a series of elements, arranged according to the order of decreasing tendency to release electrons. Elements that are located at the upper part of the electrochemical series are more electropositive and have higher tendencies to release electrons to form positive ions. For example, sodium is more electropositive than silver. Electrochemical series can be constructed based on the following principles. Potential differences between two metals in the voltaic cell. The ability of a metal to displace another metal from its salt solution. Voltaic cell is a type of cell that produces electrical energy from chemical reaction that occur inside it. When two different metals are immersed in an electrolyte solution, a potential difference is generated. The further apart the positions of the two metals in the electrochemical series, the larger the value of cell voltage that is produced. In a simple cell, the metal that is more electropositive acts as the negative terminal, while metal that is less electropositive acts as the positive terminal. In displacement reaction, a metal that is more electropositive can displace another metal, which is less electropositive from its salt solution. In displacement reaction, a metal that is more electropositive can displace another metal, which is less electropositive from its salt solution. Magnesium nitrate solution, because zinc is less electropositive than magnesium.
Electrochemical series, what it is and how it is used. In the video Measures of Electricity, we found out that different combinations of metals produce different voltages, and this depends on how strongly the metal could force its electrons to move across a cell. The electrochemical series is a list of metals and other substances arranged in rank order of how easily the atoms may lose electrons. The further apart the metals are in the electrochemical series, the higher the voltage is produced across the cell. Electrons flow along the wire from the metal higher in the electrochemical series to the metal lower down. The electropotentials are arranged in the substance's ability to donate its electrons, that is, how easily they are oxidized. All of the values are measured in volts. What do you notice about hydrogen's voltage, and what is the significance of this? Pause the video and continue when you are ready. The answer is that hydrogen has an electrode potential of 0 volts. The significance of this is that it acts as a reference. All other electrode potentials are measured against this value. It's a bit like the heights of a mountain, which are relative to the sea level. The sea level is given a height of 0 meters. Using the electrochemical series, can you predict the direction that the electrons will travel towards for the following pairs of metals? The electrons always move from the metal with the more negative electrode potential to the more positive electrode potential. Pause the video and continue when ready. For A, the answer is the electrons move from potassium to hydrogen. For B, the answer is the electrons move from zinc to copper. And for C, the answer is the electrons move from lead to mercury. You can also use the electrochemical series to predict a displacement reaction when a metal from the electrochemical series is mixed with ions of a metal lower down in the series. The atoms of the more reactive metal push their electrons onto ions of the less reactive metal. Let's consider what happens when an ion now is placed in a solution of copper sulfate. The higher up metal in the electrochemical series is the one that always displaces the ions of the lower down metal. Metals lower down in the series cannot displace more reactive metals from their solution. You can use this idea to predict whether a displacement reaction will occur. Here's a challenge. Can you explain why the ion now formed a copper coating when it was placed in a solution of copper sulfate? Pause, think and continue when ready. The correct answer is that the ion is higher in the electrochemical series, so it gave away its electrons to the less reactive copper 2 ions in solution. The ion is oxidized as shown in the equation. The copper is less reactive, so its copper 2 plus ions are forced to accept these electrons. This is called reduction. As a result, copper metal is produced and coats the now, as shown in the reaction. These two processes happen simultaneously in something called a redox reaction. In summary, the electrochemical series contains electrode potentials measured in volts, which are compared to hydrogen. The greater the difference between the two substances in the electrochemical series, the more readily the electrons move from the more reactive metal, i.e. the more negative value, to the less reactive metal, i.e. the more positive value.